Hello. So we are doing AP Physics 1 and let's start with Chapter 2. Okay. So that is describing motion. So motion is the change of state of any object. Okay. And uh, we are going to do mechanics. So mechanics is basically the study of motion of an object. And it's divided into two parts: kinematics, that we are going to do in this chapter, that deals with how objects move, and dynamics is how why objects move as the way they move. Okay. And it deals with it deals with how certain objects move in a certain way, and we discuss the force. Okay, so we'll continue with dynamics, and in this chapter particularly we are considering translation motion. Translation means moves up or down or left or right. But as we throw the ball, we know it moves up, it moves left and right, but at the same time it also rotates. So we are not considering the rotation part of it, we are considering the translation part, whether it is moving up, down, left, or right. And then we are considering here as a point mass. Like if a car is moving, we are discussing about the car or the ball. We are just taking the center of it. We are not considering like uh, mm, the first end of the car or the rear end of the car. We are not doing this. Okay. So now the next thing is the reference frame. Okay. So before that, we can discuss the types of. So what is a distance? So distance is how much an object has traveled, and displacement is the final position minus initial position. Okay, distance is the total, considering total motion of an object. Okay, how much total an object has traveled. So um, the directions we can are three types we can do. Like this is the Cartesian coordinates. Okay, this is plus x minus x plus y and negative y. Then there are relative directions. That means right, positive, left is negative, up, positive, and down, negative. Okay. And so these are the relative directions. Okay. And then there are cardinal directions. So cardinal directions are like this is east, this is north, south, and west. So displacement is the straight line distance like this. It's a straight line distance between final and the initial point. And displacement is vector. Vector means it shows magnitude and direction. And it's the final position minus initial position, or we write at delta x. Delta is a Greek word and it means change in. Okay, so this is the change in position. And this can be uh, positive or negative. Like if it is moving towards right, it will be positive. If it is moving towards left, it will be negative. It is negative. So displacement gives us direction as well as the magnitude. Whereas the distance, it is always positive and it only gives the magnitude. So, and displacement and distance, they both can be in feet, meters, and kilometers. Then the another unit is like furlong. It is the distance a team of oxen can plow without needing to rest. Okay. And then there is angstrom. These are the units. So angstrom is equal to 10 raised to power 10 meters. And then there is a rod, which is equal to 5.5 yards. Okay. And we know the distance traveled will always be greater than or equal to displacement. Because distance is the uh, total distance traveled, where displacement takes care of the direction also. So suppose if a person walks 5 kilometers east, okay, and then 2 kilometers west. So the distance would be, it is just the absolute addition of absolute value of distances. So it is 5 plus 2 is equal to 7. And displacement is equal to 5 minus 2 is equal to 3. Sorry, it doesn't have the absolute value sign. Okay. So it is the displacement will be the final position minus initial position. So 3 towards east. 3 units east. Okay. So let's go back to the book. So it is the reference frame. So reference frame and or force of reference. So any measurement of position, distance or speed, they are made, any measurement of the position, speed, distance, they are made with respect to reference. So suppose like I walked 10 kilometers east. So it is with reference to Earth, considering Earth is not moving. But the Earth is always moving, but its speed is comparatively very less. And then we consider that, um, so, bec- so we consider it is not moving, and with respect to that, our speed is 10 kilometer east. Okay. So suppose I am in a bus and bus is going with the speed of 50 miles per hour, and so this speed of bus is with respect to earth, and I'm walking inside with 1 miles per hour. So my speed with respect to earth would be 50 plus 1, 51 miles per hour, because 50 miles per hour the bus is already going, and I'm walking with. Okay. So with respect to ground, my speed is 51 miles per hour. Or suppose if we are going to the elevator and that elevator is moving with the speed of 5 miles per hour. And if I'm not moving, if I'm not walking and I'm just standing on the elevator, my speed will be 5 miles per hour. But here I'm also walking with the speed of like 0.25 miles per hour. So my speed would be like 5.25 miles per hour. Okay. So when we write about speed, it is very important that we write about the direction also, like north, east, south, west, up and down. Okay. We draw the coordinate, and this is 0, 0, x, y. Okay. So the position of an object, generally it is given by s, or it is generally, and it is given by the x coordinate. Okay. When we are moving about left and right. Okay. If the motion is vertical, then we usually use y axis. If the motion is horizontal, we use x axis, or the position is given by x coordinates, so we use x axis. Okay. So displacement gives you how far an object has traveled from the starting point. It is x final minus x initial. And it is a vector. So it gives you direction as well as the magnitude. And when can the displacement and distance both be same? Yes, they both can be same when they are when it is traveling in the same direction. Like if a person is going east, uh, traveled east 3 kilometers and then traveled east 5 kilometers. So here in both the cases, the displacement would be 3 plus 5, so 8 kilometers, and the distance also would be 8 kilometers. Absolute value of 3 plus absolute value of 5, so it will be 8 kilometers. Okay, so now next is we'll do the average velocity. So average velocity, it is the total distance. So first we'll do average speed. So average speed is again scalar. It doesn't give you the direction like distance, which doesn't give you the direction. So it is the distance traveled and time elapsed. Okay. So speed is a positive number, like distance is always positive. So speed is always positive. Okay. And then we do the average velocity. So average velocity is the displacement. So average velocity is vector. It gives you displacement over time elapsed. So this is the final position minus initial position divided by the time elapsed. So average velocity and average speed, they have the same magnitude when they are traveling in one direction. Okay. So suppose okay, suppose a person walks 50 kilometer west and then 20 kilometer east. So the distance here is absolute value of both the values. So distance is 50 plus 70 plus 20 is equal to 70. and the displacement here is final minus initial position. So if it is 50 here and 20 here, so it will be like 50 minus 20, so 30. Or we can say it started here, so it is here. So it is basically 30. And the time for, and suppose it takes uh, 10 seconds for both the moments. So the speed here is average speed will be 70 over, because it takes 5 seconds, so it will be, or 10 seconds, it will be 70 kilometer per second or per minute we can do. And the velocity, average velocity will be, it is displacement over time. So average velocity is 30 kilometer, 30 over 10. So we don't do normally in kilometer per second, but just I'm not taking that into account. I'm just showing how the display average speed and average displace, average velocity differs. Okay, and average velocity we show it with a bar. The bar here is means average. It is a standard symbol for that. So in usual case, we consider plus x to the right and minus x to the left. We can take either way, but this is a convention, and whatever we take, we have to follow it through the whole problem. We have to be consistent with that. Like for up and down, we can consider anything up as negative and down as positive. It's nothing wrong in this, but whatever we choose, we should be consistent with that during the whole problem. Well, so okay. So we can do another question based on this, like um, like suppose John goes on a eastward journey. Okay, and first is he walks east with the speed of 6 kilometers per hour, okay, for 1 hour, okay, and then he takes a tea break for 1/4 of an hour, okay, and then he continues with the speed of 5 kilometers per hour for 2 hours. So, what is the average velocity for the whole trip? And what is the displacement for the whole trip. Okay, so we know that V1 is 6 kilometers per hour. Okay, and delta T1 change in time is 1 hour. Okay, and then delta T2 is equal to, which is a tea break, is 1/4 hour. Okay, and delta T3 is 2 hours, and V3 is 5 kilometer per hour. Okay. So we can find the total distance or total ax displacement, because both the sides they were going east. So we will find the distance. So this displace here, it in 1 hour it will cover delta x1 would be, or x1 would be 6 kilometers. In 1 hour it will travel 6 kilometers. Here delta x2 is 0 and x3 is, in 2 hours it will travel 10 kilometers. So delta x will be 16 kilometers. Right? So now to find the average velocity, first we have to find the displacement, the total displacement. Okay, and or total how much it has moved. Okay, and now the t, the total time will be, this is 1 hour, this is 2 hour, 3 hour plus 1/4. So 3 and 1/4, or 13/4. So the average velocity would be 16 divided by 3 times 4 kilometer per hour. Okay. So we take the total displacement and divide it by the total time. And first we got the time for each segment, and then we divide the total distance by the total time. But we, in this case, we have to be very cautious. We cannot take the 3 velocities and divide it by 3 to get the average velocity. This is a wrong approach. We cannot add this all the 3 velocities and then divide it by 3 to get the average velocity. We have to find the total displacement and divide it by the total time elapsed. Okay. And in this case, the distance and displacement both are same, because he was walking in the same direction. Okay. Now we can, so another example we can take. Suppose John goes for a walk and leaves his house and travels 2 kilometers uh, and returns after 12, returns to his, goes to his friend's house and returns to his house in 1 hour. Okay, so in that case, what is the average speed? And what is the average velocity? So speed here will be total distance. So total distance will be 2 plus 2 kilometers, which will be 4 kilometers. Okay. And total distance over time. So it will be 1 hour. So it will be 4 kilometers per hour will be the average speed. And what will be the average velocity? It will be the displacement. So what is the displacement? Displacement is he returns back. So it is 2 minus 2 over 1. So it is 0. So average velocity will be 0 kilometer per hour. So because he started and ended in the same position, so the displacement is 0 and that's why the velocity is 0. So velocity is not equal to speed. Now the graph we can take like this. So this is a position time graph. Okay. So the slope of position time graph gives you velocity. Okay. The slope will give you velocity. So in this particular graph, the velocity is constant. Okay. But in this graph, here the velocity is constant. A person is walking with the same velocity, with a constant velocity. If this is the position and this is time, okay, so it's in the same position. So the slope here is 0, means velocity is 0 because the final and initial position are the same. Okay. And the another type of graph we can do is this. Okay. So this one shows, this is a position time graph. So this shows that a person was on left, then came at 0, 0, and then started moving right. So this shows that a person was here and with a constant velocity, it is moving towards right here. So he was at left and now it has moved towards right. Same way, if the graph is like this, okay, it shows that a person was on right. This is a position time graph. Okay. So it shows that a person was here on right, okay, and he started moving towards left. Here he reaches the 0, 0. Okay. So here the slope is negative. It means velocity is negative. Okay. Here the slope is positive. So velocity is positive. So in same way, I can make another graph also like this. So this shows that a person is moving from left to right until here, okay, and then is stationary for some time and then starts moving towards left. And this is a higher velocity. If it is like this, it means the velocity is higher than this because here the slope is more negative. Here it is less positive. Okay. Now we do, that was the average velocity. Okay. And that one thing you have to remember when you find the average velocity, we don't have to sum up the three velocities or two velocities and find average of it. Find the total distance, divide it by the total time, find the total displacement and divide it by total time. That will only give you the average velocity. So what is the instantaneous velocity? Suppose we are driving a car. That speed there shown is the instantaneous velocity. So instantaneous velocity is very important because when we are driving a car, we cannot, uh, it is not practical that we have the same velocity all through our ride. Okay. So it is instantaneous velocity is given by like this, whereas we know this means average with a bar. Okay, instantaneous velocity is the velocity at the instant. So we know average velocity is delta x over delta t. We cannot make the time delta t is zero because at an instant it is zero, but we can bring it to very close to zero. So it is like we can use little bit calculus. It's delta t tends to zero, delta x. Okay, divided by t. So this means that delta t is so less, it is approximately, it is very close to zero. It cannot be zero, otherwise it will be the error divide by zero error, but it is very close to zero. Suppose this is the graph. Okay, so this from line, the slope here, this is a position time graph. Okay, so the slope here of this red line gives you the average velocity. So when we bring it here, this, suppose we have to find at point P. So the slope here of this line CD will give you more the velocity which is more closer to the velocity at P. But the tangent drawn at point P will be the instantaneous velocity. So in some cases, constant average and instantaneous velocity are same. Suppose if velocity is of this is a graph of the this is a graph of velocity time graph. Okay, so here the velocity is same. So instantaneous velocity is same as the average velocity. Okay, but if the graph is like this, okay, so somewhere between this we find the average velocity. So here in this graph, average velocity is not same as the instantaneous velocity. So we'll study the graphs more. Like this is a velocity time graph. Okay. So the area under the curve gives you the displacement. So suppose if a car is going with a constant velocity of 5 meters per second for 5 seconds, then the displacement is the area under the graph. Okay, so it will be 5 times 5. Okay, so the distance covered will be 5 meters. Displacement will be 25 meters. And suppose if uh, if a car starts from zero uh, velocity and reaches up to 5, this is a velocity time graph, and reaches up to 5 meters per second in 5 seconds. Okay, so the displacement in this will be the area under the curve. That will be the area of the triangle. So it will be like half 5 times 5. So 25 by 2. Okay, so it will cover 25 by 2 meters. So again, V average is given by this, and this gives the instantaneous velocity. Okay. Now we can do acceleration. So, so an object whose velocity is changing, we say it is accelerating. Okay. So as I showed you the graph, when we go from 0 to 5 meters per second, as the velocity increases from 0 to 5 meters per second, as the area under the curve gives you the displacement and the slope gives you the acceleration. Okay, slope gives you acceleration it means the velocity is increasing. So average acceleration is change of velocity and time elapsed. And so again, average acceleration is given with the bar here. Okay? It is delta V. Delta means change in over delta t. Okay. And velocity is a vector, so acceleration is also a vector. And the instantaneous acceleration is given by the same. This is without the bar a and limit delta t tends to 0, delta v over delta t. This is when the delta t is so small, it is very close to 0, like the graph. Okay? The graph is like this. It's very tiny. So the tangent here gives you the instantaneous acceleration. Okay. And acceleration is a vector. It can be positive or negative as the velocity is a vector. So velocity's direction is same as the uh, direction of the displacement, but for acceleration it is not the same. So we can do a problem and then we can see it. So suppose a car accelerates from 0 to 50 uh, kilometer per hour in in half half an hour. Okay, so what will be the average acceleration? It will be v2 minus v1 over t2 minus t1. So it will be 15 minus 0 over half. So it will be 100 kilometer per hour. It means every hour the velocity is increasing with the rate of 100 kilometer per hour. It is per hour square. Okay. So acceleration tells us how quickly the velocity is changing, and velocity change tells us how uh, quickly the position is changing. So if the velocity is 0, So does it mean that acceleration is also zero? So that is not true, because when we start the car is the velocity is zero, okay, and when we start the car, it suddenly reaches 5 uh, miles per hour or 2 miles per hour. So at this instant, the velocity is zero, but the velocity changed at that instant. So acceleration is not zero. So velocity was zero when we started the car, but acceleration was not zero because the velocity changed from 0 to 5. And when the second question is, if the acceleration is zero, then would velocity be also zero? This is also not true, because when a car is going at a constant rate of 5 meters per second, okay, when the velocity is constant, then the acceleration is zero, because delta v over delta t and change in velocity is zero. So acceleration is zero. But v is not equal to zero. Actually, it is 5 meters per second. So, so another thing is the slope. Suppose this is the velocity and time graph. So in average velocity is given by when you connect the first and the last point, and the slope of this would give you the average velocity. Well, suppose if you have to find the instantaneous velocity at p, then a tangent at it will give you the instantaneous velocity. So another thing is velocity has the direction same as the displacement, but it is not the same case with the acceleration. Okay, and so if the acceleration is negative, it doesn't mean that it is slowing down. Okay, so suppose if a car is moving to the right, okay, and its initial velocity is 10 meters per second, and it takes 5 seconds to slow down, and then uh, slow down to the velocity 5 meters per second. Okay, so here the velocity was positive because it was moving to the right, and still it is positive because it is moving to the right. And what is the average acceleration? It was 10 meters. It was the final velocity. So it is 5 meters minus 10 meters per second divided by the 5. So it is minus 5 over 5, means minus 1 meter per second square. So the negative sign appears because final velocity is less than the negative is less than the initial sign. Okay. So in this case, the acceleration is towards left. Okay, because it is negative and velocities are towards right. So both of them are in the different direction. It means the object is deaccelerating. So deacceleration means slowing down. And it happens when velocity and acceleration are in the different direction. So here the acceleration was negative and the velocity was positive. Now we can take another example. Suppose a car is going, okay, with the velocity 15 meters per second towards left, okay, and uh, it reduces the velocity by to 5 meters per second in 5 seconds. So the acceleration is v2, which is minus 5. Okay. So here the velocity was negative 15 and negative 5. So negative 5, negative 15 over 5. So it will give you negative 5 plus 15 divided by 5. So it will be 2 meters per second square. So we can see that while velocities were negative, the acceleration is positive. Positive 2 meters per second square. Okay. So we say when the object is slowing down, we say deaccelerating, but it doesn't mean that acceleration is negative. They are, when they are velocity and acceleration are in opposite direction, then it means they are in the, when it means they are slowing down. When they are in the same direction, then we need, then it is the when velocity and acceleration both are either positive or both are negative, they are in the same direction, then we say that object is going fast or object is accelerating. So when the slope is steep, the object is changing velocity more rapidly, and when it is shallow, the object is not changing that rapidly. And when slope is negative, acceleration is negative, and when the slope is positive, acceleration is positive. Okay, so it is like this. Okay, so the graph of the position time graph. Okay, so this will be, suppose this is like this. Okay, so velocity Here, if we find the slope at each point, okay, we can see that it is getting more steeper. So if we draw the velocity graph on each, we see the velocity is going at a, okay, so velocity is increasing in this graph. This is a velocity time graph. Okay, so velocity is increasing. Okay, we can draw the tangents at T1, T2, T3 at C. If we draw the slope here, maybe I can draw with another color. Okay, you can see that it is increasing. Okay, and if I, so here, this, and based on this, we see that velocity is increasing with the same rate. The slope is, so the acceleration graph here will be, so acceleration is constant. So this will be the acceleration graph because the rate of change of velocity in the slope is same. Okay. So now the other graph here is, suppose it's like this, and this is the position time graph. Okay, so here the we see if we draw the tangent, okay, so velocity is high at the beginning and then it becomes low, low, and low, and it becomes here 0 at this point. Okay, so this, the graph will be like this. So tangent and is high and continuously decreases and becomes 0 at time t. So the slope of velocity is negative and acceleration here will be like this. So the moment is towards right in the whole because position and velocity graph are positive. Okay, so moment is right here towards it. So this is the acceleration graph. Now we can take one more graph like this. So suppose this is, okay, so this is position and time. Okay. So velocity is positive here all the time and the moment is towards right all the time. But we can see that if we draw the tangent, it will be, okay, so velocity is rising here, then it becomes 0 at this point, and then it starts decreasing. So this is velocity time graph. Okay. So the tangents in the first part, they are positive, okay, and in the second part, they are negative. Yeah. Okay. And the acceleration in the same graph would here be, it is positive because velocity uh, is increasing, and after that, since velocity is decreasing, it is negative. Okay. Now, the next thing is we can do the motion at constant acceleration, and we will develop the three kinematics equations. They are very important. So we will examine the motion at constant acceleration. So we know the average velocity, it is delta x over delta t, which is equal to x2 minus x1 over t2 minus t1. Okay. And here, because we always take the time for time t is equal to 0, that's why we will just write x2 over minus x1 over t. So the acceleration here is v minus v0 over t. V final over v0 over 2. So this is acceleration, which is change in velocity over time t. So this is at. So v final is equal to v0 plus at. Okay. Now we know what is the average velocity. Okay. If we take this equation and write it, it will be like this if we put it as x final minus x initial over t. So we can say that x final is x initial plus v bar t. So here it is the average velocity we are taking into account. Okay, this is the average velocity. So what is the average velocity? Because velocity is increasing at uniform rate. So it is between the initial and final velocity. We drew the graph like this, and here the average velocity is v initial plus v final over 2. Okay, so this is, so the x final is equal to xi or initial plus v bar is vi plus vf by 2. Okay, and from this equation t would be, okay, now Okay. So the last equation we developed was Vx is equal to x final is equal to x0 plus v bar t. Okay. And so x0 plus vf plus v0 by 2. Okay. And time is equal to, okay, and then vf is equal to v0 plus at. So x0 is equal to v final is equal to v0 plus at plus v0 by 2t. So this will give us v0t plus half at square. So this is a very useful kinematic equation. So we have derived up till now two. One was this, second is this. Okay. And the third one is, we know from here T is equal to Vf minus V0 by A. So when we write x final is equal to x0 plus V bar T, we can write it as x0 plus V0 plus Vf by 2 is equal to Vf minus V0 by A. Okay. Suppose xf minus xo is we'll bring this here. So this will become Vf square minus Vo square over 2a. Okay. So this will be, if we bring it here, it will be, that's xf minus xo, we write it as delta x. Okay. Or the distance traveled, suppose we write it as x. So this will become 2as. So Vf square minus Vo square. So Vf square is equal to Vo square plus 2as. So this is the third kinematic equation. So these three equations are very important. So these are the three very important equations. And remember, they have the acceleration is considered, it's the constant in each. So this is equation number 1, 2, and 3. Okay. And the another one is when the acceleration is constant, v bar is equal to v0 or v final plus v0 by 2. And whenever you solve any problems, please do not uh, round it up before, only the round it up the final answers. Okay, do not round in the middle of the problem. So in the next class, we'll do some problems using these equations. Okay, thank you. Thanks for joining. So we are going to do a study about free fall, and suppose we drop two balls. Okay, one is 10 kg and one is 5 kg, and from a height of 10 feet, which will come faster, or which will touch the ground faster. So actually both of them would reach at the same time because the height is same and the acceleration due to gravity, okay, which is minus g, and g is 9.8 meter per second square. So they both will reach the ground at the same time because it is not dependent on the mass. So this is a free fall. When object is in free fall, when the only force acting on it is force of gravity, okay, and it is not touching any object, okay, and there is no air resistance, or it is in the vacuum, like we can breathe, okay, so no air resistance. So if it follows these conditions, we say it is a free fall. And free fall is not like if it is only coming down. If we throw a ball also up, that is also considered a free fall. Okay, so G is always positive. Remember, G is always positive. It is 9.8 meter per second square. Acceleration due to gravity in y direction, that is negative. And when it is also known as UAM, because when a object is in free fall, then the acceleration is constant. Okay, so we can use all the four UAM equations we derived it earlier. Okay, so it is not dependent on mass. All objects, regardless of mass, will have the same acceleration. So if they are made to fall from the same height and the acceleration due to gravity is same, then they will reach uh, uh, ground at the same time. Though acceleration due to gravity varies from location to location, but at the same place, we can consider it as a constant 9.8 meter per second square. Okay. So the distance it covers, or the distance it falls, is directly proportional to the square of the time. Okay, so as we discussed, the speed of the object falling down is not proportional to its mass. It is rather the distance covered, or the distance by which it falls, is proportional to the square of the time. So suppose if we make a if we take a brick, okay, and if we take a paper, okay, and if we drop them, we see that the paper will go like this, and it will take more time to reach here, but the brick would reach faster. But if we crumble the paper and if we put the brick and in the apps, they both will reach at the same time because they are it depends on the surface area. So the air resistance, they are both are facing the same air resistance, so they both will fall at the same time. And suppose if we put these both of these in a vacuum, then they both will fall in the same time regardless of their surface area because there is no air resistance. So all objects, whether light or heavy, will fall with the same acceleration, which is acceleration due to gravity in the absence of air. So at a given location on the Earth and in the absence of air resistance, all objects will fall with the same constant acceleration. Okay, that is G is equal to 9.8 meter per second square. In British units, we use 32 feet per second square. So, actually, G will vary slightly according to the latitude and elevation, but these variations are very small. So mostly we ignore that. Okay. And when we do the problems, we can either choose Y to be positive up or and negative down, or negative up and positive down. But whatever we choose, we have to be consistent throughout the problem. Okay, so now let's take one example. So suppose a ball is dropped from a tower, okay, and what will it will have, how far it will cover after 1 second. So how much distance it would have covered after 1 second, 2 seconds, and 3 seconds. Okay, so and we'll ignore the air resistance. So whenever we say dropped, it means our V initial is 0. Whenever we say thrown, it means there is some value of V initial. It has some value. Okay, so whenever we say dropped, it means initial value is 0. Now we'll use the second equation, which is V initial times plus half AT square. Okay, in this, so first finding after 1 second, so it will be 0 plus half, so it will be half, and I'm considering up as positive, so acceleration will be negative. So it will be, and if the tower is this much, uh, so we'll consider this as negative. So it will be negative 9.8 times 1 square. So it will be negative 4.9 meters. So after 1 second, it will fall back 4.9 meters. Okay. Now, after 2 seconds, it will be uh, 10.2 square. So it will be negative 19.6 meters. So it would have fallen 19.6 meters. Okay. And after 3 seconds, it will be half negative 9.8 times 3 square. So it will be negative 44.1 meters. Okay. So we can see if we draw the curve, we can see that the y and t graph comes out to be like this. So the curve is, it bends upward because y is directly proportional to t square in this. Okay. Now in the same question, if we take some, we say that the ball is thrown downwards. In that case, when we say it's question number 2, and suppose if we say that ball is thrown downwards with the velocity 3 meters per second. So in this case, we can say so in this case, instead of drop, we are using it is thrown. So what would be its position after 1 or 2 seconds? Okay. So here, when it is drop, we are considering up as positive and down as negative. So it will be V0t plus half a t square. Okay. So this will be after 1 second, it will be 3 times 1 minus V0 is also negative and A is also negative and this is 1. So it is negative 11.8 meters. Sorry, it is negative 2, negative 4.9, 4.9. Okay, so it is negative 6.9 meters. Okay, so it will come down by, it will be down by negative 6.9 meters. So we can see that when we threw the ball with initial velocity 0, it traveled a less distance. Okay, then what happens after 2 seconds? So this will be minus 2 times 2. It will be negative 4, negative 19.6. Okay, so it will be negative 8. Okay, so we can see as we that now it is covering more distance. When the initial velocity was 0, it traveled, it could cover less distance. Now it is covering more distance when when the ball was thrown with the velocity 2 meters per second square. So the speed or the velocity is increasing linearly in time with, it is always 2 meters per second higher than the uh, than of the dropped ball. Okay. Now we can take another example. Now suppose we throw a ball upward with the velocity of, suppose if we throw ball upward with velocity of 10 meters per second. So we have to calculate how high it goes. So we do not worry about how we throw because we are worried about the motion after we throw it. Okay. So again, considering y to be positive in the upward direction and y to be negative in the downward direction. So here a is equal to negative g, okay, which is equal to negative 9.8 meter per second square. So when we throw a ball from A, So acceleration due to gravity is downward. So we will have a negative sign. A is equal to acceleration due to gravity in my y direction is downward. So when we throw a ball from position A, suppose, and we catch it at C, velocity is upward, but gravity always acts downwards. Okay, acceleration due to gravity. So here the velocity is highest when we throw it, and then it becomes less, and it is zero at B, and then it increases but in a negative direction. And then it is at the same velocity at A and C are the same, but at A velocity is positive, at C velocity is negative, and gravity is always acting down. Okay. Acceleration due to gravity is always acting down. So if we have to find how high it will go, we know that velocity at the top is zero. Okay, and velocity, so VI, initial velocity was 10 meters per second. Okay, and final velocity is zero. Suppose we take only till the half, because the time, because the motion is symmetrical, so the time required to go up is same as the time required to come down. Okay, and suppose we have, and while finding how high it will go, we see that velocity final here is zero, or we can say at the top, velocity at the top, Vt is zero. Okay, so we'll use this equation where V final, V at the top, is equal to V initial square plus 2as. Okay, so this will be Vt square minus Vi square over 2a. Okay, so it will be 100 over 19.6. So this will be around, so this will be around 5.1 meters. Okay, so that much it will go up. Now, if we want, because as we know, velocity when we throw it is highest, then it becomes less, and at the highest point where it could reach, it becomes zero, and then it starts increasing again, and at C it is the same velocity. Suppose if we throw at A and then again catch, it will be the same velocity, but it will be in the negative direction. So the distance covered, the highest distance uh, uh, it went was 5.1. Okay, so it reaches the height of 5.1 above our head. Now, how much time it takes to reach at the highest point or to reach and come back at C? So that we can do, two ways, because we have the initial velocity at 10 meters per second, and the ball is thrown at A, and it reaches B and then it comes down at C. So if we want the total time, we can say we can use this equation by final is equal to y initial plus v0 t plus half at square. So if we both a0 and ac are same, so suppose if it started with 0, we'll put this and then 10 meters and t we have to find, and then negative 9.8 and t square. Okay, so this will be it will be 10t minus 4.9 t square is equal to 0. So t is equal to 10 minus 4.9 t. That's 10 over 4.9. So it will be 2.04 or t is equal to 0. So t is equal to 0 is obvious when we start, it starts with the time 0 and it returns back when the time it is t is equal to 2.04 seconds. Or we can say the other way we can find out is because the motion is symmetrical, it starts from A, the motion between A to B and B to C is symmetrical. So we can consider the Vf is equal to V0 plus AT. Vf is 0. V0 is 10 minus 9.8 T. So T here will be 10 over okay. So it will be 10 over 9.8, which will be 1.02. Okay. So the time required here will be 1.02 seconds. So this is the time to go up. So this is the time for A to B. So from B to C will be again 1.02 seconds. So the total will be 2.04. So it comes out to be same. So either we can use this equation or we can use this equation. Both are same. And we have ignored air resistance in this case. And we do not consider the throwing actions because when the thrower's hand is touching the ball and the acceleration is not g and it is not a free fall because the condition to be in free fall is it should not be touching any object. So another thing we need to take care of is when we throw a ball from A to B and B to C, and it comes B to C. At B, we know the velocity is 0. So first thing is, do velocity and acceleration are in the same direction always. So it is not like that. When we throw the ball, velocity is up, but the acceleration due to gravity is down. And when it is, G is always down because it is towards the center of the earth. But when the ball is coming down, the velocity is down and the gravity is also acceleration due to gravity is down. Okay. And the other thing is that at the point B, the velocity is zero. Okay. Velocity at top is zero. So does the acceleration is also zero at B? No, it is not zero. Because what is acceleration? It is the rate of change of velocity. So if it would have been zero, then there will be no change and the ball will hang up in the air. But it is not like that. It comes down. So though the velocity at the top point is zero, acceleration at the top is not zero. It changes. Otherwise, the ball would have stayed there, and acceleration of the gravity is always pointing towards Earth even when the ball is coming down. We can take another example. Suppose we are standing on the building and we throw a ball up with the velocity 10 meters per second. Okay, so it goes up, it reaches a point, and then it comes down. So how long will it take, will the ball take to reach to the ground? And it is thrown with the initial velocity of VR. So time to reach ground. So it will be y. We'll use this equation y is equal to y0 plus v0 t plus half at. So suppose the height of this is 100 meters. Okay, so we so this is 100. Okay, we take up as positive, y up as positive, and down as negative. So this is 0. Okay. So this is 0 plus 10 times t minus 9.8 meter, and this is t square. Okay, so we can use this as we can use quadratic equation to find its answer. I use the formula t is equal to minus b plus minus b square minus 4ac over 2a. So this gives us t as 5.65 and negative 3.6. So since we want to find the time, so this 3.6 may be the equation when it would have if it would have started here. What we are concerned about the time it reaches ground. So that is 5.06 seconds or 5.65 seconds. Okay. So that is the time. That is the answer what we are thinking about when how much time it will take to come down. So it takes 5.6 5 seconds. And so when it leaves hand, it goes up and then it comes down in 5.65 seconds. So as we have done earlier also, but I just want to repeat the slope of the position time graph. The slope gives us velocity. So in this, the velocity is constant. The slope here gives us velocity and velocity is constant. Okay. Okay. And suppose if the moment if an object is traveling and when the velocity is not constant like this, velocity at t1 and t2, here it is x1 and x2. Okay. So the velocity is delta x over delta t. Okay. So that is, this gives you the chord drawn here gives you the average velocity. And suppose if we take, so this is between t1 and t2, and suppose if we find between any point t3, then this steep, this is more steeper. So the velocity between average velocity between T1 and T3 is higher than T1 and T2 because the graph is more steeper. And when we find, suppose if we have to find the velocity at point P, the tangent drawn here gives us the instantaneous velocity at point P. So suppose the graph is like this. Okay, so here the tangent velocity at this point, this is rising, this is more steeper, so it is higher. So velocity at P2 is higher than P1 because it is more steeper. At P3 it is 0 because it is the tangent is a horizontal line, and at P4 it it has a value at negative direction because the slope is negative. Okay. And then suppose two bus are going with uh, and with a going with a velocity of 200 kilometer per hour and in 20 seconds and 20 seconds. Okay. And then calculate, if we have to calculate the, and this is the graph. Okay. This is a bus A and bus B. So the average acceleration, what is the average acceleration in this? The average acceleration in both is same because they covered the because they have the same average, the same velocity. They reach to the same velocity for the same interval of the time, same interval of time. But the instantaneous acceleration is the slope. So we can see in the beginning the slope of B is steeper, of A is steeper. So it has a greater acceleration, and later on the slope at B becomes more steeper, so it has a greater acceleration. And we can say a bus A is always going faster than B, so it will cover more distance. And also we can say that the area is it is shaded. Okay, so we'll continue with the next concepts in the next class. Thank you so much. So we are going to do the free fall. We are going to learn about free fall of the objects. So an object is in free fall when the only force acting on it is the force of gravity. Okay, so an object is in free fall if it is not touching any object, any other object. Right? And there is no air resistance, or we can say that, or the air, it is in vacuum, we can breathe, like, so no air resistance. Okay, so, and by free fall, we don't mean that it is going down. When we throw a ball up, that is also considered a free fall because it is not touching any object. It is uh, it, only force acting on it is force of gravity. Okay, and considering there is no air resistance. Okay, so these are the, and suppose we take two balls. Okay, and one is like 15 kg and the other is 5 kg. Okay. And they are put at the height of 10 feet. So which one would reach the ground first? So both, considering, because both have the same acceleration due to gravity, which is negative 9.8 meter per second square, and they will both reach at the same time. Okay, so all objects will fall with the same constant acceleration in the absence of air or other air resistance. Okay, so that is not dependent on the mass. The speed of falling of an object is not proportional to the mass. So all objects, whether heavy or light, they will fall with the same acceleration in the absence of air. Like suppose if we take a paper and a stone, so which one would reach fast? Stone would reach faster than the paper because uh, this has a less surface area to fight with the air resistance. Okay, and the paper would take a little longer time. Okay, because the surface area, so it is not dependent on the mass. Okay, but if we crumble the paper, which is having approximately the same surface area as of the stone, they both would reach at the same time. Okay, because they will undergo the same air resistance in that case. So at a given location on the earth and in the absence of air resistance, all objects will fall with the same constant acceleration, that is g 9.8 meter per second square. Okay, and this is SI unit, and the British unit is 32 feet per second square.